Thank you very much for having me today. So I'm going to talk about data scientists' two favorite subjects, infrastructure and DevOps. I know everybody's super excited about that. So I'm going to cover a little bit about how we think there might be a blueprint for building an operating system for AI. And so I'm really happy that we came right after Amanda, because she talked about all this amazing stuff that they're doing. Just think about the infrastructure that needs to be behind this to run at that scale. With the ups and downs, the speed at which it needs to work. So this is where these type of things get interesting. Bloomberg is not a customer of us yet, but so just FYI on that. So Algorithmia, we make state-of-the-art algorithms discoverable and accessible to everyone. So we actually started the company with this idea that as more and more machine learning goes into everyday applications, discovering the right algorithm, being able to use it, the right model, the right function, and then be able to access it in the right stack, in the right language, what I want to use it, is going to be really important. So how we ended up in this, a little bit of background on myself. I've spent my entire career building tools for doing data analysis. Probably the most famous one that you probably heard of is this spreadsheet. You have a love-hate relationship made by Microsoft. So that's a little bit about me. So Algorithmia.com is AI/ML scalable infrastructure on demand with a marketplace. So what we do is we have this functions as a service for machine learning and deep learning. We work on CPUs, we work on GPUs. We have a discoverable live inventory of AI that people from across the globe put on our system, everything from image classifiers to NLP models across the board. We make it monetizable. More importantly, we make it composable, so all these components can actually be tied together. And finally, the real goal is to make every developer on Earth be able to make their application intelligent. The word intelligence, a loaded word, but essentially use data science and machine learning in their everyday application. And we support a whole bunch of 10 different languages, different stacks across the board. So one of the big things to think about is like, we have 63,000 developers that use our platform, over 4,800 independent different algorithms, and everything from pattern recognition, classifying user data, understanding audio, deriving language meaning across the board, and in all these languages. So what's the infrastructure and problem behind it, which is really what I'm going to be touching on today. So 4,800 different algorithms. Actually, if you think about the different versions, every single one of them's version, we're actually dealing with over 50,000 different functions at any given time that need to be able to deploy it and run on the infrastructure. Each algorithm at any time can be called from 1 to 1,000 times a second. It fluctuates with absolutely no DevOps involved from the user's perspective. We sit to a strict latency of under 15 milliseconds of overhead throughout an entire system. And interesting enough, we have to run in every language or in any architecture, because not only do we run our system in the cloud, we actually also run it on premise for certain customers as well. So I'm going to rewind a little bit and talk about like kind of the big thing of like, if we were going to go to build an operating system for AI, what would that look like? And AI has two distinct phases, and training and inference. And I'm really going to concentrate on kind of the inference or like classification part today. Lots of processing power involved. As of today, a lot of heterogeneous hardware. We compute on CPUs, we compute on GPUs, TPUs, ASICs. And in most cases, we're limited by compute rather than bandwidth. I realize that we had somebody talking about satellite imagery, so there is other situations where like bandwidth is actually a huge problem as well. But in most cases, it's actually limited by compute. And then this is one of my favorite quotes actually from our CTO, which is kind of like our battle cry, which is TensorFlow is open source, but actually scaling it is not. And we'll talk a little bit about those concepts here. So really high level training. So in the world of data science, so usually this is long compute cycles. May take hours, might take weeks in some cases with some neural nets. It takes a massive amount of data. Usually it's from a fixed load. So you kind of know, hey, I'm going to go process 100,000 images. I'm going to go process 1,000,000 images. It's stateful, obviously. You need to be checkpoints on the weights. You need checkpoints on how the process goes. And it's usually done by a single user. In some cases, it's data scientists on their laptops. In some cases, it might be with a little bit more beefy infrastructure doing on GPUs and on AWS or in Azure. So we like to think of it as this is analysis of a dev toolchain. Usually pick your framework. So maybe you're doing Keras or you're doing TensorFlow. Maybe you're using scikit-learn. You iterate multiple times over and over again, and then when you're done, you have this model, which again, you'll continue improving over time, but like the end result is kind of what comes out of it. It's usually a single user transaction. So we're going to pick an easy use case. So Xing Yang has made an app that actually recognizes foods, and it's fully trained, and it works on his machine. So he's super happy. He can take a picture. It tells him if it's a hot dog or it's not a hot dog. So fantastic. So he deploys his model onto a GPU-enabled server. TensorFlow gets it up and running. Great. Everything's working great. Overnight, boom, hits the top of the App Store. Suddenly, there's hundreds of thousands of people downloading his app. And now what? So servers overloaded, many apps trying to figure out if this is a hot dog or not a hot dog. Servers crashing, bad problem overall. So really what we're trying to do here is like, how do we actually scale up that so that you can actually have these type of applications and go and become popular in that way? So I'm going to talk about two different concepts. And just quickly, how many people in the room know about microservices in general? Okay, good, great. How about serverless? It's not my favorite word, by the way, but anyway, we'll go. So the microservices, it's designed of a system, independently deployable, loosely coupled services. So the advantages are maintainability, scalability, and rolling deployments. On the other side of the equation, we have serverless, which is this kind of like encapsulation, starting and stopping of singular functions per request with a just-in-time compute model. And the advantages are cost efficiency, concurrency is actually built in, the speed of development, and improve latency. And so what I want to do is today is going to give a little bit of a blueprint of why I'm going to make a case where I actually think that AI and machine learning are the killer apps for serverless microservices. And that's kind of where I'm going to guide us today. So although the training aspect is the owner's the data scientist, and it's usually a one-person thing, and building and iterating over a model is similar to building an app, we think that the inference side of things is actually owned by DevOps. And the infrastructure teams, because it's short compute bursts, and you're going to do classifications very quickly. Maybe it's an image, maybe it's a bunch of text. It's going to be elastic. There's going to be fluctuations of up and down of like how the traffic as it's coming in. If you think about, especially if you're doing things like on Twitter or like over certain big events, it's stateless. The most recent classification is now really relevant to the previous classification or the next classification for a specific model. And more importantly, it involves multiple users, in some cases hundreds of users, thousands of users at the same time. So we make a case for inference really being, running concurrent models requires task scheduling on different OSs, on different infrastructures, and it's a lot more similar to an OS. So I'm going to talk a little bit about, so in the world of training, Metal, VM, this long compute cycle, fixed load, full single user, perfect. Now, in the world of inference, short compute bursts and stateless, there's this technology called containers that are super light. They can be spun up very, very quickly. They can be killed very, very quickly. So they actually work really well for this stage of doing inference. The second one, which is I want an elastic compute. So if during, Xing Yang's app is going to get super popular at lunchtime because people want to understand if this is a hot dog or not a hot dog, then I might want to scale up my entire infrastructure to be able to serve that. And then as that infrastructure goes down, I want to be able to scale it down quickly again. So there's this technology that was actually developed by Google for how they actually do the scaling of their infrastructure called Kubernetes, which is fairly well accepted these days. And that gives you that elastic computation power. And then the multiple users, actually abstracting over a REST API so it can be universally called, no matter in what language you're building your application, no matter in what stack you're actually running it. If I can abstract it over a REST API endpoint, I can now actually call it from those applications. So why microservices? Well, one, it gives me elasticity. Two, so I can go up and down. It becomes scalable. Three, it's actually software agnostic. So I can actually deploy this maybe in a data center inside AWS, maybe in a data center inside GCP, maybe I want to do it on premise. And more importantly, I can actually now track the data, which ends up being in a lot of cases the heaviest component of these pipelines. And finally, the hardware agnostic part. So why serverless? And these are, I talked about cost efficiency, concurrency built in, and improved latency. So let's actually go look in a traditional architecture what Xing Yang's app might look like. So in this case, maybe in the max amount of calls, it's going to be getting something like 140 calls a second. Maybe I need 37 GPUs. So if I'm actually doing capacity planning, which a lot of times you've done, like I actually need to go build for the max, right? Which means everything here that's not in graph is complete waste of either computational resource, or if I'm actually using it in the cloud, I'm just paying. I'm sure Amazon is not complaining, but you're just paying for cycles that you don't need. So in the case of, so we made some back-of-the-napkin calculation. Maybe this costs you $25,000 to run a month. Using serverless, we can actually track as the demand comes in. We can use our load balancers to quickly initiate and replicate these models over the entire infrastructure, going up and down with the demand, allowing for savings of up to 85% of the infrastructure cost that I'm actually going to be deploying in this case. So if I can actually achieve spinning up and down these models in a quick way over a horizontal infrastructure, then there's real savings to be had by just moving towards a serverless model. So concurrency. So as soon as I start having hundreds, potentially thousands of applications trying to classify their hot dogs, I realize how ridiculous this example is, by the way. Hitting a load balancer, that load balancer can actually start doing is replicating those models horizontally so that we can actually serve more. And remember, these are stateless. So I can serially be sending these images to all of these models, classifying them without actually being involved with anybody else. And I can do it in a very, very quick form, especially when I have an elastic infrastructure under it. The other thing is latency. So there's a design principle that we use personally at Algorithmia, which is data is heavy and expensive to move, but compute is light and cheap. We can actually throw compute across data centers. We can throw compute across hybrids from on-premise to burst into the cloud. But actually moving the data sets is what you should try to avoid doing. But computing them in the same data center, that actually works. So if I want to have a great experience, if I want my hot dog classification app to have an amazing experience, it doesn't matter where on earth I'm going to be hitting. I want that concurrency, and I want to be able to have it the closest endpoint to where I'm sending that classification so everybody has that experience. So I talked about containers, and I talked about using Kubernetes, and I talked about using the REST API, and that's kind of table stakes for building in a system. The part of a system, an OS for AI, that really becomes interesting is kind of the deeper down things that become relevant. Things like GPU memory management and job scheduling and cloud abstraction. How do I make sure that this pipeline that I built is going to work everywhere that I need it to work? So the definition of an operating system is a software that supports a computer's basic functions, but really important is at scheduling tasks, executing applications, and controlling peripherals. So the way that we look at it is scheduling tasks, executing models and functions, and then actually being able to control different heterogeneous hardware as you're actually going and building that out. So if we talk about, if we want to split it in kind of two things, the kernel and the shell services. The shell services are things like discoverability, authentication, monitoring, and instrumentation. So like in our particular example of algorithmia.com, if you went to our website, you interact with the website, you see the algorithms, the functions, and models. You can use them, you can work around them, and then that's kind of the shell services. But the really interesting stuff is the kernel. So the elastic scale that prioritizes and automatically can optimize execution of concurrent jobs. The runtime abstraction, support any programming language, framework, including interoperability between stacks, and the cloud abstraction, which is providing portability for these algorithms to work in any public cloud or private cloud. Remember, our mission in the beginning was to make state-of-the-art algorithms discoverable and accessible no matter where you need them. So elastic scale, what does this mean? API comes in through the API load balancer, hits an API server says, where's their availability? Where can I initiate this container? Where can I send it to? Is it in one region? Is it in another? Do I need a GPU? Do I need a CPU? And actually go build that. So if you actually manage to build this all out, congratulations, you've essentially built AWS Lambda. Second, composability. One of the things that's forgotten a lot of times is actually all of these AI systems are usually ensembles, or they're usually large pipelines that get built. So we probably wouldn't have built just a classifier to classify food. We probably would have built a composition of classifiers. One, in this case, let's say a fruit or veggie classifier. If we actually made it into a fruit, we would go into the fruit classifier because that would be more accurate. So composability is critical for AI workflows because of data processing pipelines and ensembles. So then it might look like something like this. Knowing that algorithm A always calls algorithm B, and algorithm A consumes X CPU in memory, and algorithm B consumes X CPU in memory. Therefore, our OS needs to be smart enough to understand how to actually put these things on the resources, reduce network latency, increase the cluster utilization, and build dependency graphs so that when you're actually deploying these at scale, all these containers and all these classifiers are moving together as they get scaled. Runtime abstraction. Maybe I start in Python and scikit-learn. Maybe the second one's actually written in Java. Maybe I have a TensorFlow model that's using a bit of R. The ability to actually put these all together is extremely important for a generic OS for AI. And finally, cloud abstraction. Build once, not per cloud or per hardware. So if I'm actually going to be calling data in a particular client, it doesn't matter if that data is in S3. It doesn't mean if it's HDFS, if it's Dropbox. I should have a complete abstraction layer between all of those that allow me to reuse the exact same components no matter where the architecture is being deployed on. So, in summary, what makes an OS for AI? It's stack agnostic, it's composable, it's self-optimizing, it's auto-scaling, it's monitorable, and it's discoverable. Thank you. If you want to try Algorithmia for free, you can use that code, by the way. Free stuff.
Very cool. Thank you very much. Who do you sell to?
So we kind of have two different industries that well, not industries, two kind of different sectors. So we have our public cloud service, which, as I said, we have about 63,000 developers. It tends to be mid-market technology companies, individual developers, smaller shops, ones that are okay using a SaaS product. And then this infrastructure that we built for Algorithmia.com, we package it up and deploy it inside large enterprises. And the industries that we focus on are usually regulated, so intelligence agencies, financial services, pharmaceutical companies, large pharma, and advanced manufacturing tend to be our customers there.
Oh, interesting. Those guys are happy to work with a cloud solution?
And we actually deploy it behind their firewall.
Oh, it's all on-prem.
So everything that architecture is meant for saying, hey, we have these teams of data scientists, we're having the problem of actually getting into production, so we build that all inside their firewall.
Very cool. Okay. All right, let's open up to questions that people have time to ask. Want to hear?
Fascinating stuff, and really, because I'm in this space. So when I'm looking at what you're doing, you've basically taken the DevOps and you've given the ability to deploy these models. Most of what I see from clients is the big problems are really on the training side. They can't even get the model out, right? So it seems like you've kind of divorced yourself, and you call it inference, I call it scoring component. You know, how do clients come to you and say, really, I have a scoring problem. I don't necessarily, because I'll give two names out, data science experience from IBM and Amazon SageMaker. I'm sure your two biggest competitors, and those are not small competitors. So can you kind of expound on that?
Yeah. So I think there's, so we do somewhat divorce, and I don't think you can truly divorce, a training from production and inference, because in a lot of cases it's a cycle, right? Where you have humans re-annotating, you're retraining. So the way we look at production machine learning, we treat it like a CI/CD pipeline, where there's going to be a component that's doing the training, maybe it's distributing over many GPUs. There's going to be a result. That result is going to be a model that's going to get pushed into our platform, and we're going to do the scaling until the scoring gets done on one way or another, and then comes back down. To your point about kind of the individual cloud competitors and their products, we're probably the only product out there that does serverless over GPUs, and it's really important from a price and a performance perspective. The other thing is that we actually do cross-cloud. So imagine if you're a large enterprise, you're probably betting on more than one cloud provider. We're giving you one model deployment technology that's actually going out to all the different clouds, including your on-premise service as well.
Just one more quick follow-up. How many clients are you actually seeing that are deploying across multiple clouds? Because I don't see it today.
We actually have quite a few. It obviously is a self-selecting group, but we do see quite a bit.
One in the back over there.
Thanks. So for your marketplace, do you do benchmarking between, like, for example, computer vision? You have so many choices. So how do you maybe inform the customer of what is a good algorithm? And that feeds into the idea of the spin wheel, maybe involving the community more to help make those decisions.
Absolutely, great question. So we have a couple of different ways where we do it. Well, one is that we believe in this principle that when people ask us, what's the best algorithm for X? And I always have a hard time with that question because I'm like, well, what's your data set? Like, what are you trying to do? Are you going for speed? Are you going for accuracy? Because it really depends based on what you're trying to achieve. So what we have built into the platform is kind of this social proof, which is very similar to what you would see in GitHub, voting up and down, commenting system saying, hey, it worked really well for this, it didn't work well for that. But at the end of the day, it's very hard for anybody but you to make a decision on, is this good for your use case? Because in sometimes a very fast classification that gives you only 80% accuracy is absolutely okay. And in other cases, you're going to want to go for the absolute accuracy because you can't make a mistake because it could cause the tumbling of, markets. So like at the end of the day, the actual data set and the business use case that you're pursuing is the one that's going to determine, is this good for you or not? So taking that principle in mind, what we've done is we made it as easy as possible for testing these algorithms. So you don't have to deploy libraries, you don't have to download dependencies. There's an API endpoint, I can start sending data to it, and I can actually make that determination.
Tell us about the company and the team.
Sure.
What did you guys start? What's the history? It's always fascinating.
Yeah. So we're based out of Seattle, headquartered in Seattle. Have a small office here in New York. Team of 24 people at this point. Raised about $13.5 million. Our latest round was done by Google's AI fund. So it's a fund dedicated to investing in AI companies.
Just Gradient?
Gradient, yeah. The GV again. I don't know why they did pick that. I'm not in their branding department. And again, like really the company is built around people who are machine learning experts and infrastructure experts. And one of the things that we saw is that there's really like not a lot of people dedicating themselves to understanding what the world of DevOps for AI is going to kind of look like. And that's really where we, what we've set out to do.
All right. One last one from Tony over there.
Just a very quick question, which is, what are your relationships to the cloud providers? Do you have any formal relationships with them?
Yeah. So we, for every dollar that we, that we make, the infrastructure provider under us is making more than that dollar. So it's a really good relationship for both of us. The more we see a world where we want to move as many workloads to the cloud as possible. Like, we see that as a good thing, not only because it helps us get our scheduler better and create liquidity on the system, but also because the elasticity of the cloud is great. So we have good relationships with all the cloud providers, and some of them we actually do co-selling experiences with them, where we're informing their sales forces to say, hey, this is a product that exists on AWS, this is a product that exists on Azure, and you can actually go ahead and use it inside your own private accounts. And so that's kind of like our, it's a good relationship, I would say. It's a win-win.
All right, wonderful. On this note, we had a wonderful evening, 4 great talks. Please join me in thanking both Bloomberg, our host, and our speakers. And as you guys know, we have food and drinks out there, so please enjoy, and we'll see you at the next one. Thanks very much.